Alright, now let's move on to the first application. Shortest distance from point to plane. Find the shortest distance from this point over here to this plane over here. So this plane is in the Cartesian form. So we know that the normal vector is just 1, 1, negative 1. That's our normal vector. I can also write my plane in terms of the normal vector form, r dot 1, 1, negative 1 equals to 2. Now first up, what I want to do is I want to find this point over here, f. Because if I can find this point f, again, this will be 90 degrees, and hence finding this vector between a and f will give me the shortest distance from the point to the plane. So how do we do this? First of all, I'm going to find the equation of the line that passes through a and f. And then I can find the intersection point between the line and the plane, which we know to be f. For this line L, actually we have a positional vector a already. And if you see, the normal vector is actually one of the possible directional vectors of this line. So we can take the normal vector as the directional vector. Now these two r's over here just represent a general point. So I can substitute the line into the plane in order to find the intersection point. So what I get is 1 plus lambda, negative 3 plus lambda, and 2 minus lambda. This is basically your equation of the line. And then I'm going to substitute it into the plane. So I have 1, 1, negative 1 equals to 2. Again, what I'm doing is substituting this part into this part, because this r represents a general point on the plane and line respectively. So by finding the value of lambda where this is true, is basically finding the intersection point between the plane and the line, which gives us the point f, because that's our intersection point between the plane and this line. So if we evaluate the dot product, we get lambda equals to 2. And now we can find our point f by just substituting lambda equals to 2. The next thing I can do is find vector AF or find vector FA, both are the same thing. The magnitude of either of them will still give you the shortest distance. Let me just find AF then. We'll take OF minus OA. I'll get this as 2, 2, negative 2. And finding the magnitude, this is just 2 square plus 2 square plus negative 2 square, which is equals to root 12 or 2 root 3 units. So that over here is your shortest distance between the point and the plane. Now I'm going to introduce a formula to find the perpendicular distance from the origin to the plane. So we have our origin O here, and we want to find this perpendicular distance over here. So the distance from the origin to the plane will always be d over the magnitude of the normal vector. This modular sign is just to make sure that the distance is positive. Now this actually also lends us to the distance between parallel planes. Let's say I have the equation of plane pi 1 as r dot n1 equals to d1 and pi 2 to be r dot n2 equals to d2. Then the distance between these two parallel planes is just d1 over the magnitude of n1 minus d2 over the magnitude of n2. Again, this modular sign over here is just to make sure that the distance is positive. These two formula are not in your formula booklet, but these are good to remember so that you can solve questions really quickly. Now we're moving on to the third application, which will be the angle between line and plane and the angle between two planes. Let's start off first with the angle between the line and plane. I have this line here with directional vector d. I have this plane here with the normal vector n. Now we can find something in terms of alpha. Although this is not the angle between line and plane, if you see alpha is just your angle between the directional vector and your normal vector. We can do cosine alpha equals to d dot n over magnitude of d magnitude of n. Again, this is us using the dot product formula. And the modular sign here is just to make sure that your angle is acute. Now how does cosine alpha relate to theta, which is the actual angle between this line and the plane over here? If you see this already, cosine alpha is just equals to cosine 90 degrees minus theta. Why is this so? If you look at this triangle over here that I've drawn, cosine of alpha is just cosine 90 degrees minus theta. And hence, cosine 90 degrees minus theta will just give you this. where theta, again, is your angle between the line and the plane. Now we try to find the angle between two planes. So I have this plane over here, and this plane over here. I'm just drawing this as a line, but you can imagine the plane extending out from the screen and into the screen. And that will make a 2D plane. Same for this one. And we have our two normal vectors, n1 and n2 for the two planes. Now, instinctually, what we like to do is find the angle between the two normal vectors. And again, we can use the dot product formula to find this. Now what I want you to see is the angle between these two normal vectors is actually the exact same angle between the two planes. And if you're curious why, in this quadrilateral over here, A plus theta make 180 degrees. As well as this straight line over here, A plus theta also make 180 degrees. That's why the theta are both the same. So that's how to find the angle between two planes. In case you forgot, here's the formula for the angle between two lines. Now, we have our final application, which relates to systems of linear equations. Now, I didn't make a video on systems of linear equations because I'm going to add it in here. Systems of linear equations are especially important when we're solving intersection points for two planes and three planes. First of all, let's solve this question. Find the line of intersection between this plane and this plane. Now what this is basically simultaneous equations. So what I'm going to do is try to solve the simultaneous equation. What I want to do is maybe eliminate a variable. So if I take equation 1 plus equation 2, this will get us 3x minus 2z equals to 10. And let me just make x the subject of the formula. And if I sub this into equation 1, what I can do is find y in terms of z. So this will give us y equals to 8 over 3 plus 7 over 3z. Now I'm just going to write z equals to z here, and I want you to see something. Doesn't this look somewhat familiar? Doesn't this look like the parametric form of a line with z as your parameter? So what I'm just going to do is take z to be my parameter, or why not, I just change it to lambda because it looks nicer. So I have 10 over 3, 8 over 3 and 0 as your point, and then I have lambda 2/3, 7/3, 1. If we have these sort of questions in paper 2, we can also solve this with a GDC. What I can do to solve this system of linear equations is go to the menu, click on algebra, and then go to solve system of linear equations. Here we have two equations and three variables, x, y, and z. So let's key that in. Now we can key in our two equations that we had from earlier. And after keying these two equations in, we can press enter, and that's our answer. Now if you look at this is very similar to the parametric form that we got earlier. This is saying that x equals to this, y equals to this, and z equals to this. In this case, C2 just represents lambda. So we have x equals to 10 over 3 plus 2 over 3 lambda, y equals to 8 over 3 plus 7 over 3 lambda, and z equals to lambda. So that's your line of intersection, which is just the same as the answer that we got earlier. Now the next part of systems of linear equations is solving three planes. This question asks us to find the point of intersection between the three planes, x plus 4y plus 11z equals to 7, x plus 6y plus 17z equals to 9, and x plus 4y plus 8z equals to 4. So let's say we have equation 1 and equation 2. What we want to do to eliminate, let's say, a variable x is take equation 2 minus equation 1. And after that, that eliminates our variable x. I'm going to introduce to you a new method of solving systems of linear equations, which is called the Gaussian elimination. What I'm going to do is copy down the coefficients of x, y, and z into the first three columns over here. So I'll write 1, 4, and 11. And for the last row, I'll copy down the constant. So this is equals to 7, so I'm going to write down 7. Similarly, I'm going to write down 1, 6, and 17, and then the constant, 9. I'm going to write down 1, 4, and 8, and then the constant 4. Now, similar to how we want to eliminate a variable for simultaneous equations, what we want to do for this Gaussian elimination is also to eliminate a variable. So remember how earlier we took equation 2 minus equation 1? Right here, I'm going to take row 2 minus row 1. Now the purpose of doing a Gaussian elimination is actually to get this triangle of zeros over here. So after we do this Gaussian elimination, we should get this triangle of zeros in these 3 spots. I'm going to write down the first row again, 1, 4, 11, and 7. And then I'm going to do row 2 minus row 1. I'll get 1 minus 1 to get 0 here. Then I'll take 6 minus 4, which is just 2. Then I'll take 17 minus 11, which is 6. And finally 9 minus 7, which is 2. Now as you can see, after I've done this process by the way is called row reduction. You can see that I've gotten my first 0 in this spot over here. Our next goal is to get these 2 zeros over here. So in the third row, what I can do is actually take row 3 minus row 1. And as you can see, this very nicely gives me my 2 zeros over here, because I take 1 minus 1 and 4 minus 4. Next up I have 8 minus 11, which is negative 3, and 4 minus 7, which is also negative 3. So how do we interpret this after we get our triangle of zeros over here? Remember that this tells you the coefficient of x, this tells you the coefficient of y, and this column tells you the coefficient of z. So how we interpret this is negative 3z equals to negative 3. And this simply gives us z equals to 1. Now that we have z equals to 1, we can substitute that into this equation over here, which says that 2y plus 6z equals to 2. If we substitute z equals to 1, we should get that y equals to negative 2. Our first equation states that x plus 4y plus 11z equals to 7. And if we substitute this value of z and this value of y, we should get that x equals to 4. Now the Gaussian elimination, whether we do it manually or using the GDC, which I'll show you how to do later, can help you to show if the system of linear equations has either one, infinite, or no solutions. After we do our Gaussian elimination, we should get something like this, with 0, 0, a, and b, where a and b are just constants. Remember, we will have our triangle of zeros after we finish our Gaussian elimination. In each of these 3 scenarios, the bottom row, just the bottom row, can help us to deduce whether we will have one, infinite, or no solutions. In the case that we only have one unique solution, we have that a is not equals to 0. So earlier if we look at our Gaussian elimination, we have that a, this value a, is not equals to 0. Hence, we'll have one unique solution. Geometrically, this one unique solution can be seen as a point of intersection between our 3 planes. So we have our 3 planes over here in blue, yellow, and green. And these 3 planes will meet at this point of intersection, which is our one unique solution. Now next, if a equals to 0 and b equals to 0, meaning our last row should look like 0, 0, 0, 0, this means that we'll have an infinitely many number of solutions. Geometrically, this will look like a line of intersection. So again, we have our 3 planes and they intersect on this line. And this line provides us with our infinitely many solutions. Our final case is when a equals to 0 but b is not equals to 0. To give you a bit of intuition on why this is so, imagine our last row, 0x plus 0y plus 0z equals to a non-zero number. If you look at this equation, there's no value of x, y, and z that can fulfill this equation. Hence, there'll be no solution. And geometrically, this means that the 3 planes that we have no point of intersection. So this is what it could look like. There are no points of intersections between these 3 planes. Now let's see how solving these systems of linear equations looks like in the GDC. We can see that there's a unique solution over here. Now what about if I want to show that there's a unique solution in the form of RREF? What I'm going to do is type in RREF, then I'm going to put a bracket, and I'm going to come here over to this button and click on this matrix. Now we will want 3 rows and 4 columns so that we can key in all these into the matrix. So remember what we're doing is keying in all the coefficients of x, y, and z. So we have 1, 4, and 11. And then we have this constant term over here, 7, which we'll key in here. So we have 1, 6, 17, 9, 1, 4, 8, 4. And we can press enter. And if you look at our bottom row, this is the form when we have one unique solution. So showing this means that we are able to show that we have one unique solution. Now we have our next set of equations here, and we can see again that this is a line of intersection. If we want to show that there are an infinite number of solutions for this system, we can use the RREF form again. So we key in all the coefficients. And look, our last row is 0, 0, 0, 0, which is the form for having an infinite number of solutions, or a line of intersection. So if we show this, this is how we show that there's an infinite set of solutions. Now we have this last set of linear equations, and keying it into linsolve, we can see that there's no solution found. Again, how do we show it in RREF form? After keying in all the coefficients, I can press enter, and look, our last line is 0, 0, 0, 1. Now this matches the same form as having no solutions. So by showing this, this shows that there's no solution to this system of linear equations. Here's the summary sheet for planes. I hope you found this helpful. Thank you for watching.